Hello, my name is Sepideh Nikookar. I'm a third-year CS PhD candidate at NJIT and part of the Big Data Analytics Lab. The paper I will be presenting is titled Cooperative Route Planning Framework for Multiple Distributed Assets in Maritime Applications. It is a collaborative work between our lab, the University of Connecticut, and the US Naval Research Laboratory. This work focuses on adaptive route planning for multiple ships in a way to minimize time and fuel consumption while avoiding collision. Each ship has its own corresponding starting location as well as its own limitation in terms of sensing radius, engine capacity, and maximum speed. What we intend to do in this work is to see how we can plan routes of the ships such that all the ships reach the unknown destination by consuming minimum fuel and time without collision. This work comes from the general premise of complex environments, as there are multiple objectives and complex constraints. Decision-making is uncertain, and the design solution should be adaptive. It also has many compelling applications, ranging from search to rescue, traffic monitoring, and automated vehicles routing. It serves as a decision support tool to help end users to make decisions. And finally, it is considered data management for AI because of its memory and CPU bottleneck. The first overarching challenges in achieving our goal is related to the modeling. We need to design simultaneous decision-making model for multiple agents, which incorporates context in the decision-making and considers different objectives and constraints for each agent. In terms of computational challenges, we are dealing with memory and CPU bottlenecks. And in terms of algorithmic challenges, we need to design generic solutions that can scale and overcome CPU and memory bottleneck. To the best of our knowledge, the existing works fall under one of the two extremes of manual solutions or automated solutions. Exploratory data analysis, or EDA, is a notable example of automated solutions, which is used in different works for designing the reinforcement learning agents to generate exploratory sessions for data scientists or to discover user groups, as well as for complex task recommendation. Route planning is also another automated solutions which use an approximate dynamic programming method for navigating a single ship in uncertain environments. In terms of our contributions, we model the problem as a team discrete Markov decision process. We also propose a multi-agent, multi-objective reinforcement learning framework and study efficiency opportunities. We perform an extensive experimental evaluations using multiple real-world and synthetic grids. And finally, our work has been deployed for use by the Naval Research Laboratory, Monterey, for water space management. Formally speaking, in the route planning problem, we want to navigate and cooperative ships with respective starting points that are distributed over a discrete grid to discover an initially unknown destination and optimize multiple objectives while satisfying constraints. In this problem, our objectives are minimizing maximum time to reach destination, as well as minimizing total fuel consumption by all the ships. As a constraint, ships should avoid collision anytime during the exploration. Based on our assumption, each ship has maximum speed and it can observe the grid up to its sensing radius. Ships make decisions by going to one of the neighboring nodes or wait at the same place to avoid collision. Two ships communicate with each other periodically to exchange their location at a fixed time interval or when one of them has found the destination. In this presentation, I'm going to use ships and assets interchangeably. Up to this point, I talked about our motivation and the problem we are aiming to solve. Now what I have left is to talk about proposed solution, approximation functions, experimental results, as well as conclusion and future work. We model the route planning problem as a team discrete Markov decision process, which instead corresponds to the current location of all the ships at a given time, and it has exponential size with respect to the size of the grid and number of the ships. Action is the decision to transit to one of the neighboring points at a specific speed or wait at the same place to avoid collision. There is also a reward associated with each transition. We designed 3 reward functions. The first one is the exploration reward, which captures how much of the unexplored grid an asset can sense. The other one is a time reward, which is the inverse of the maximum time each asset needs as a part of the action. And the last one is the fuel reward, which is proportional to the inverse of total fuel consumption by all the ships. We use this equation in order to calculate fuel consumption per unit distance. Ships move in a direction that maximizes the exploration reward, and they move at a speed that maximizes the average of time and fuel reward. Let me bring our real example back and consider only 2 assets of it, their respective current position and their visited path after 2 moves. Each asset can sense the grid up to its sensing radius, which is based on the distance, and it is represented by double circuit green and blue nodes for asset 1 and asset 2 respectively. Asset 1 can go to one of the sensed neighboring nodes from the initial position, and it can also move at 3 different speeds. Generally, it's better to move toward the direction that more of not yet sensed nodes will be explored as long as collision are avoided. So from the initial position, asset 1 take action A0 because more nodes will be sensed from the new positions and it moves at the speed 2. Similarly, from this point, asset 2 takes action A0 prime and go to the point 66 because more 3 nodes will be sensed from this position, and it moves at a speed 2 because it minimizes the average of time and fuel consumption. After all the assets took their action, at the end of the iteration, we need to calculate all 3 rewards for the corresponding action. We propose a multi-agent, multi-objective reinforcement learning, or MAMOREL in short, for cooperative route planning under constraint. MAMOREL has 3 interactive modules. The first one is a teammate module, which captures the probability distribution of the belief of each asset on the locations and actions of the other assets. When one asset makes its own decision, it also needs to predict the actions and locations of the other assets through an appropriate internal model. Teammate module is designed to represent this internal model, and it will be updated periodically after each asset observes the locations and actions of the other assets. The other module is the action selection module, which enables distributed decision-making by each asset to optimize multiple objectives while satisfying constraints. The last one is a learning module, which learns functional approximation based on different moves of the assets through a Q function. It is infeasible to compute MAMOREL exactly in a realistic setting because of its memory and CPU bottlenecks. For example, in order to run MAMOREL on a grid of 400 nodes for only 2 assets, it needs a 38.5 gigabyte of memory, and it takes around 3.5 hours to run on a highly powerful server. Because MAMOREL needs to store very large P and Q tables with exponential size. So in order to address these bottlenecks, we propose function approximation based on linear regression and neural network that avoid pre-computing tables. We also leverage limited training data for approximation. The CPU bottleneck arises from the need to learn effectively in a setting with an exponential action and a state space. The linear regression-based function approximation is designed with extensive feature engineering efforts to effectively approximate P and Q values. It also works in a way that instead of storing the entire P and Q tables, predict a value function as a linear combination of the features. Features are handcrafted, and they are the degree of current location, distance to the other ships, direction toward unsensed nodes, direction toward destination, as well as the speed of the assets. Some features are useful before the goal is discovered, such as direction toward unsensed node, and some are useful afterward, like direction toward destination. The neural network function approximation uses the same set of features as linear regression, and it is trained by collecting the P and Q values and their corresponding feature values for each possible action state pair. We conducted extensive experimental evaluations to validate our framework using 2 different data sets. We have the Caribbean grid, North America shore grid, Atlantic grid as part of our real world grids. We also generated some synthetic grids by varying nodes between 100 to 1000 and varying ages between 500 to 2000. We compare approximate model with 4 different baselines. One of them is the approximate model with partial knowledge, which is actually a modified version of the approximate model. In the approximate model with partial knowledge, destination is inside the region that the assets are aware of, but they don't know the exact location of the destination. So all the assets use Dijkstra to reach the boundary of the region. Then they use the approximate model inside the region to explore it and find the destination. The other one is a baseline one that assets plan their routes one by one in a non-simultaneous round-robin fashion. This baseline requires less fuel because of a longer wait time at each node and avoiding unnecessary moves at the expenses of taking longer time to reach destination. The other one is baseline 2, which uses the same reward function as our problem, and assets plan their routes independently without considering the actions of the other. Based on its nature, this method is prone to collisions. And the last one is the random walk baseline, in which assets, action, and speed are decided randomly from a uniform probability function. We compare approximate model with the exact model as well as baselines. Our experiments show Memorial suffers from significant memory and CPU bottlenecks. But all of these bottlenecks are addressed in approximate model through function approximation, and it can produce reasonable performance to the exact model while being an order of magnitude faster. Based on the design, based on how baseline 2 is designed, it results in asset collisions for more than 90–70% of the runs. Our experiments demonstrate approximate model is more effective than its neural network counterpart, and it is 15 times faster in training time. The objective value functions of approximate model are very close to model. We also observe that approximate model is robust to different parameters, and it is computationally efficient in terms of running time. Approximate model is also a suitable choice for transfer learning. To sum up, we formalize the route planning problem as a team discrete Markov decision process and propose a multi-agent, multi-objective reinforcement learning framework as a solution. We also study data management opportunities through function approximation based on linear regression and neural network. We also experimentally demonstrate Memorial's effectiveness on multiple real-world and synthetic grids. Memorial is also deployed inside Templar to enable simultaneous route planning for multiple assets that are robust to uncertainty under multiple contexts. As an extension of our work, we have planned to investigate further efficiency issues using rollout, which is a one-time policy iteration approach. We also want to analyze the post-deployment data collected through click and eye tracking behavior of the users to quantify its ease of use, flexibility, and robustness in multi-asset decision-making. Thanks for listening, and I'm happy to take any questions.